Our map of the cosmos is built on a foundation of error. We are about to journey through 35 space discoveries that do not just add to our knowledge, they shatter it. From planets made of diamond to cosmic voids that defy logic, each finding pulls at the threads of reality itself. By the end, you will see the universe not as a settled picture, but as a living puzzle where every answer reveals a deeper mystery. How did a star end up older than everything? Why are galaxies streaming toward nothing? This is not a tour of what we know. It is an expedition into what we cannot explain. What part of your reality are you ready to question first? Our journey begins with a force so immense it is dragging our galaxy toward a point of absolute darkness. This is the Great Attractor, a gravitational anomaly of staggering power located roughly 250 million light-years away in the direction of the constellations Centaurus and Hydra. It is not a single object but a dense knot of mass, a gravitational focal point pulling our Milky Way and thousands of other galaxies in a vast, silent river through space. We are moving toward it at over 2 million kilometers per hour, caught in a current we cannot see and do not fully understand. The true mystery, however, lies in what hides it. The Great Attractor sits directly behind the plane of our own galaxy, in a region astronomers poetically call the zone of avoidance. Here, thick clouds of cosmic dust and stars from the Milky Way's core completely block our optical view. It is like trying to see a distant city through a dense, permanent fog. For decades, this zone was a blind spot on our cosmic maps, a blank space where our telescopes were useless. How could we map the universe if a quarter of it was permanently obscured? The discovery of the Great Attractor came not from light but from motion. By meticulously measuring the subtle redshifts and blueshifts of galaxies, how their light stretches or compresses as they move, scientists detected a vast, coherent flow. Thousands of galaxies, including our own, were all streaming in the same direction, toward an unseen something with the gravitational pull of tens of thousands of Milky Ways. This realization was a profound shock to our models of cosmic structure. The universe was not evenly sprinkled with galaxies. Something titanic was warping the landscape on a scale we had barely begun to comprehend. The Great Attractor hints at structures of unimaginable mass, cosmic architecture built from dark matter and galaxy clusters in configurations we are only starting to perceive. It forces us to admit that our local corner of the universe is not calm or random, but caught in a gravitational tide driven by hidden giants. What else lies hidden in the zone of avoidance, and what does this colossal pull tell us about the fate of our galactic neighborhood? But the Great Attractor was not the end of the story, it was merely the first clue. As scientists peered deeper into this mysterious galactic current, they found something that made the anomaly seem almost local. They discovered the dark flow. This is not a flow of dark matter or dark energy. It is a dark flow of entire galaxy clusters, hundreds of millions of light years across, all moving in concert like leaves on a river toward a point on the cosmic map that does not exist. This motion cannot be explained by any visible structure within our observable universe, not even by the Great Attractor. The data, gathered by studying the subtle distortions in the cosmic microwave background, the afterglow of the Big Bang itself, revealed that these immense structures are streaming at incredible speeds toward a region of space beyond the edge of everything we can see. It is as if you stood in a vast, flat field and felt a powerful, steady wind, but every tree, every blade of grass for miles around was perfectly still. The source of that wind is not on the field. It is somewhere over the horizon, unseen and unimaginably vast. This finding directly challenges one of cosmology's most fundamental assumptions, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. In simpler terms, it means the universe should look roughly the same in every direction and no place should be special. The dark flow suggests something is not the same. It hints that our entire observable universe, all 93 billion light-years of it, might be feeling the gravitational tug of something colossal that lies outside of it. What could possibly exert such an influence from beyond the cosmic horizon? Theorists are left with staggering possibilities. One is that the dark flow is evidence of a cosmic structure from a pre-Big Bang era, a relic imprint of something that existed before our universe began. Another, even more mind-bending idea is that we are feeling the pull of a neighboring universe, a separate bubble of reality in a vast multiverse brushing against our own. This is not science fiction, it is a data-driven mystery. The dark flow tells us that our cosmic home might not be an isolated island, but one shoreline of a continent we cannot yet see. If true, what does that say about the very nature of our existence and the boundaries of reality itself? The unsettling pull of the dark flow suggests we are not alone in a grander structure, but it confronts us with a silence closer to home that is equally profound. This is the heart of the Fermi paradox, a discovery not of something out there, but of a glaring contradiction right here. The numbers are overwhelmingly in favor of life. Our galaxy contains hundreds of billions of stars. Most of those stars have planets, and a significant fraction of those planets orbit in the habitable zone where liquid water could exist. The ingredients for life, the complex organic molecules, are scattered everywhere, even in the vast clouds between stars. Given the age of the universe, over 13 billion years, intelligent civilizations should have had more than enough time to arise, spread, and make their presence known across the Milky Way. And yet, when we listen, we hear nothing but static. When we look, we see no megastructures, no signatures of cosmic engineering, no visitors. The universe appears empty, silent, and strangely still. This paradox is not just a puzzle about them, it is a fundamental discovery about us and our reality. It forces us to question our most basic assumptions about life, intelligence, and technology. Why does the cosmos seem so barren when everything we know suggests it should be teeming? One of the most sobering answers is the Great Filter hypothesis. This idea proposes that there is at least one nearly insurmountable barrier, a filter that prevents life from progressing to the stage of interstellar colonization. The terrifying question is where this filter lies. Is it behind us? Are we the rare, lucky ones who survived the perilous jump from simple chemistry to complex multicellular life, or is the filter still ahead of us? Perhaps every civilization that reaches our level of technological advancement inevitably destroys itself with its own creations, through nuclear war, engineered pandemics, or runaway artificial intelligence. The silence of the heavens in this view is a cemetery quiet. Other solutions are less grim but no less reality-bending. Perhaps advanced civilizations are everywhere, but their technology is so far beyond our comprehension that we cannot recognize it. Their communications might not use radio waves at all, but something we have not yet imagined, like neutrino modulation or gravitational wave whispers. Their structures might not be solid objects, but manipulations of spacetime itself, invisible to our instruments. They might have transcended physical form entirely, uploading their consciousness into a digital realm, leaving the material universe a quiet backwater. Or consider the zoo hypothesis, the idea that we live in a kind of galactic wildlife preserve. More advanced civilizations know we are here but have agreed not to interfere, allowing us to develop naturally until we reach a certain maturity. Our entire planet is being observed with a prime directive so perfect we cannot detect it. Each possible answer to the Fermi paradox reshapes our understanding of reality. It challenges the notion that intelligence is a natural endpoint of evolution, or that expansion is the inevitable goal of a species. That profound silence we hear when we point our telescopes at the stars is not an absence of data, it is a mirror. It reflects back our own hopes, our fears, and our deepest uncertainties about what it means to be a thinking creature in a vast and seemingly indifferent cosmos. The question is no longer just where is everybody, but what does their absence or their hidden presence tell us about the ultimate fate of minds like our own? That profound cosmic silence was broken once by a shout. On the evening of August 15, 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the heavens. The data was printed out on long, continuous sheets of paper, rows of letters and numbers corresponding to signal strength. A few days later, volunteer astronomer Jerry Amon was reviewing the printouts when his eye caught a sequence of characters so extraordinary he circled it in red pen and wrote one word beside it. Wow! The signal lasted for 72 seconds, the exact duration the telescope's fixed antenna could observe a single point in the sky as the Earth rotated. It came from the direction of the constellation Sagittarius near the star group Chi Sagittarii. What made it astonishing was its intensity and its frequency. It blazed at 30 times the background noise, a sharp, powerful spike on an otherwise quiet line. Crucially, it was transmitted at the frequency of 1,420 MHz, a radio band that is protected by international agreement. On Earth, this frequency is reserved for scientific purposes, specifically for listening to the universe, because it is a quiet channel where natural cosmic noise from hydrogen, the most common element, is minimal. It is, in essence, the universe's own designated listening frequency. The WOW signal had every characteristic scientists had predicted for an artificial interstellar broadcast. It was narrowband, meaning it was focused on one specific frequency. Unlike the broad spectrum of noise from stars or nebulae, it appeared and then vanished as the telescope's beam moved, just as a signal from a distant, fixed source should. And it came from a seemingly empty patch of space. In that one brief moment, it felt like a cosmic door had been flung open, a beacon aimed directly at us. Yet that door slammed shut just as quickly. Despite decades of follow-up observations by countless telescopes, including the most powerful arrays on the planet, the signal has never been heard again. Not a whisper, not an echo. Its solitary, brilliant flash remains utterly unique. This singular event is a different kind of discovery, one that challenges reality not by what it is, but by what it implies. The WOW signal forces us to confront the possibility of a universe that is not uniformly silent, but punctuated by incredibly rare, fleeting, and perhaps deliberate events. It shatters the comfortable assumption that if aliens are out there, they would be broadcasting continuously, like a cosmic radio station we could tune into anytime. What if they are not? What if interstellar communication is not a constant conversation, but a series of isolated, monumental shouts across the void, separated by centuries or millennia? Perhaps the signal was a one-time burst from a long-dead civilization, a final monument that reached us just as its builders faded away. Maybe it was a targeted message meant for someone else that swept across our solar system by chance, a cosmic wrong number. Or it could have been an incredibly focused, powerful beacon that simply is not pointing at us anymore, scanning the galaxy like a lighthouse beam that illuminated Earth for just 72 seconds. The profound frustration and enduring mystery of the WOW signal is that it provides the strongest evidence we have ever had for an artificial extraterrestrial origin, yet it offers no way to verify it. It is a data point of one. It teaches us that our search for intelligence may be looking for the wrong thing, expecting persistent patterns in a universe that might operate on a scale of time and intention we can scarcely grasp. That one circled word on a sheet of paper, WOW, is a permanent question mark in the margin of our understanding, a reminder that the cosmos might speak only once, and we must be listening at exactly the right moment to hear it. While the WOW signal was a fleeting shout, another mystery announced itself with a persistent, rhythmic flicker. This is Tabby's star, officially known as KIC 8462852, a seemingly ordinary star over 1,000 light-years away in the constellation Cygnus. Its discovery did not come from a radio telescope, but from the Kepler Space Telescope, which stared at it for years, measuring its brightness with incredible precision to hunt for planets. Astronomers expected to see the gentle, predictable dips in light caused by a planet passing in front of the star, a transit lasting a few hours and repeating like clockwork. What they found instead was chaos. Tabby's star dims in ways that defy all natural explanation. Its light drops by staggering amounts, sometimes over 20%, which is far too much for even a Jupiter-sized planet to cause. These dips are not regular, they are erratic with no discernible pattern, lasting for days or even weeks at a time. Some are sharp and steep, others are slow and uneven. It is as if something massive, irregular, and utterly opaque is drifting in front of the star in a bizarre, complex dance. The immediate challenge to reality here is to our models of stellar systems. We have a very good understanding of how planets form and behave. They are spherical, they orbit in predictable ellipses, and they cause symmetrical, repeating transits. Tabby's star obeys none of these rules. Whatever is blocking its light is not a simple sphere, and it is not following a clean, Keplerian orbit. This forces astronomers to consider possibilities that stretch the boundaries of known astrophysics. The first, more natural explanations are already extreme. One leading theory is a colossal swarm of comets, perhaps millions of them, shattered and on wildly eccentric orbits, creating a vast, clumpy cloud of dust and ice that intermittently blocks the star's light. Another idea involves a recent planetary collision, leaving a sprawling field of debris that has not yet settled into a ring. Yet these scenarios struggle to explain the sheer depth and irregularity of the dimming, and the fact that data also suggests the star's overall brightness has been slowly, mysteriously fading for over a century. This is where the theory that captured the public's imagination enters, the idea of alien megastructures, specifically a Dyson sphere or more likely, a Dyson swarm. This is a hypothetical concept where an advanced civilization, needing immense amounts of energy, would construct a vast array of solar collectors in orbit around their star, capturing a significant fraction of its light output. Such a structure would be incomplete and uneven, with panels and habitats moving independently, creating exactly the kind of irregular, deep, and achingly strange light curve we observe. While scientists overwhelmingly consider natural causes more likely, the very fact that an alien megastructure is a plausible discussion point is revolutionary. Tabby's star forces a profound admission that our catalogue of cosmic phenomena is incomplete. There are shapes and structures in the universe we have not yet imagined, whether they are born from natural chaos or intelligent design. It teaches us that when we go looking for planets, we must be prepared to find something else entirely, something that does not fit in any of our boxes. The star's silent, erratic blinking is a message written in shadows, a puzzle where every potential solution rewrites a chapter in the book of cosmic possibilities. The strange flicker of Tabby's star taught us to expect the unexpected, but the cosmos delivered a visitor that defied every expectation. In October 2017, a telescope in Hawaii spotted a faint point of light moving at breathtaking speed. It was not from our solar system. This was Oumuamua, the first interstellar object ever detected passing through our cosmic neighborhood. Its name, from Hawaiian, appropriately means scout or messenger from the distant past. The data revealed a shape that was utterly bizarre. Oumuamua was not round like an asteroid or a comet. Based on how its brightness changed dramatically as it tumbled, scientists deduced it was highly elongated, shaped like a pancake or perhaps a cigar, with dimensions estimated at up to 10 times longer than it was wide. Nothing naturally occurring in our solar system looks quite like that, but the real shock came from its motion. As Oumuamua sped away from the sun, something was wrong. Its trajectory could not be explained by gravity alone. It was accelerating ever so slightly, as if an unseen force was giving it a gentle push. This non-gravitational acceleration is the hallmark of a comet. When a comet's icy surface heats up near a star, it vents gas and dust in jets which act like tiny thrusters. The problem was, Oumuamua showed no visible signs of this activity. No surrounding cloud of gas, no dusty tail. It was dark, reddish, and completely inert to our telescopes. So what was pushing it? The scientific debate was and remains fierce. The leading natural explanation is that it was a comet after all, but an exotic one. Perhaps it was made of very pure, solid nitrogen or hydrogen ice, which could outgas without leaving the dusty debris that forms a visible tail. Or maybe it was a fractal-like aggregate of dust, a cosmic dust bunny so porous and lightweight that sunlight itself could push on it, a phenomenon called radiation pressure. These are plausible ideas, but they require materials and formations not commonly seen in our own system. The mystery of its acceleration, combined with its unprecedented shape, opened the door for more speculative thoughts. Could Oumuamua be artificial? The most famous proponent of this idea, Harvard astronomer Avi Loeb, suggested it might be a light sail, a thin piece of technology designed to be propelled by starlight. Its flat, pancake-like shape and its acceleration from sunlight pressure would fit that profile remarkably well. While most astronomers strongly favor a natural origin, the very fact that such a discussion reached the highest levels of science is a testament to how profoundly Oumuamua challenged our reality. It forced us to confront a simple, staggering fact: interstellar space is not empty. It is filled with travelers, and we have only just begun to see them. Oumuamua was a glimpse of the building blocks of other star systems, a sample of cosmic chemistry from a factory we have never visited. Its silent, tumbling passage was a message in itself, telling us that our solar system is not an island, but a stop on a highway of drifting wonders. What other shapes are sailing the dark between the stars, and what will the next visitor teach us about the diversity of worlds we have yet to imagine? Oumuamua was a visitor from a distant stellar forge, but our oldest cosmic relic holds a different kind of anomaly, one frozen into the fabric of the universe itself. This is the cosmic microwave background cold spot, a chilling mystery imprinted on the sky from the dawn of time. The cosmic microwave background is the faint, uniform glow that fills the entire universe, the cooled and stretched afterglow of the Big Bang's first light, released when the cosmos was just 380,000 years old. It is the most perfect baby picture we have of reality. When scientists mapped this glow with incredible precision, they expected to see a nearly uniform tapestry, with only tiny, random variations in temperature, the seeds that would one day grow into galaxies. But one region in the constellation Eridanus stood out like a bruise. It is far colder than the surrounding area, and it is enormous, spanning nearly 1 billion light-years across. The odds of such a large and frigid patch forming by random chance in our standard model of cosmology are less than 1 in 200. It is a statistical ghost, a place where the universe seems to have broken its own rules. This cold spot is not just a curiosity, it is a potential crack in the foundation of our understanding. The leading theory within conventional physics is that it might be a supervoid, an immense, mostly empty region of space where matter is unusually scarce. As light travels through such a void, it can lose energy, stretching to longer, cooler wavelengths in a process called the integrated Sachs-Wolfe effect. But there is a problem. To produce a cold spot this pronounced, the void would need to be staggeringly vast and profoundly empty, far beyond any other structure we have observed. It would be a cosmic desert on a scale that challenges our models of how matter clumped together after the Big Bang. The search for this supervoid has yielded ambiguous results, leaving the mystery wide open. This gap in explanation has allowed for more radical, breathtaking possibilities. One of the most profound is the idea that the cold spot is a scar from a collision with another universe. In the theory of eternal inflation, our universe is just one bubble in a vast, frothing multiverse. These bubble universes can, on rare occasions, bump into one another as they expand. If our young, hot universe had brushed against the boundary of a neighboring bubble, the energy of that collision could have drained away from that region of space, leaving it colder than the rest. In this scenario, the cold spot is not a flaw in our map, but a window. It is a fossilized imprint of something outside our entire reality, a place where the walls of our cosmic bubble are thinner, marked by contact with another realm with entirely different laws of physics. Whether it is a titanic void or a multiverse bruise, the cold spot forces a humbling realization. Our most successful theory of the universe's origin, cosmic inflation, which explains its overall smoothness and structure, might be incomplete. This cold patch on the sky is a whisper from the first moments of everything, suggesting that the story of creation was more violent, more complex, or more interconnected than we ever dared to dream. What else is written in that ancient light, and what other borders of reality might we find if we know how to look? The ancient cold spot whispers of a violent past, but the modern cosmos screams with sudden, brilliant violence. These are fast radio bursts, or FRB, perhaps the most explosive and enigmatic signals in the universe. For a few thousandths of a second, a source from billions of light years away unleashes a radio pulse so powerful it can outshine an entire galaxy, channeling more energy than our sun emits in 80 years. Then, just as suddenly, it vanishes. When the first one was discovered in archived data in 2007, astronomers were baffled. It was a single, spectacular spike, a cosmic flash in the pan. The leading theory was a one-time cataclysm, something like a neutron star collapsing into a black hole or two incredibly dense objects smashing together in a final, fatal merger. These events would be the universe's most powerful fireworks, but they would only happen once. Then, everything changed. In 2016, astronomers found an FRB source that did the impossible. It repeated, not on a schedule, not predictably, but it flashed again and again from the same patch of sky. This single discovery shattered the cataclysmic model. Whatever was producing these bursts was not destroying itself. It was surviving, and it was capable of unleashing its titanic energy over and over. This forced a complete rethink of what kind of object or phenomenon could be so violently energetic yet so durable. The search for an explanation leads to some of the most extreme physics in the cosmos. The current prime suspect is a type of neutron star called a magnetar. Imagine the core of a giant star, crushed into a sphere the size of a city but weighing more than our sun, and then imbued with a magnetic field 1 trillion times stronger than anything on Earth. This magnetic field is so intense it can literally crack the star's solid crust, causing starquakes that release tsunamis of energy, potentially powering these brief, universe-spanning radio shouts. We have even detected an FRB from a known magnetar within our own galaxy, providing a crucial piece of evidence, yet the mystery is far from solved. The repeating bursts show complex patterns, with periods of frenetic activity followed by long stretches of silence. Some sources have been traced to the turbulent outskirts of distant galaxies, environments ripe for cosmic violence. Others, perplexingly, seem to come from quieter, more serene galactic neighborhoods. This diversity suggests there might be multiple ways to cook up an FRB, a whole zoo of cosmic engines we are only beginning to catalog. The sheer power and brevity of the signals, however, inevitably raise a more speculative question. Could they be artificial? The idea of an alien origin is not the first choice for scientists, but it is a tantalizing thought experiment. A burst that powerful and that brief would be an excellent beacon for interstellar communication, a lighthouse pulse that could be seen across the universe. Or perhaps it is evidence of unimaginable technology, like a light sail being pushed to near light speed by a planet-sized power transmitter, with a leakage of energy we detect as a millisecond flash. While natural explanations like magnetars are far more likely, the very existence of FRBs challenges our knowledge of high-energy astrophysics at its limits. They are reminders that the universe is capable of concentrating and releasing energy in ways we are still struggling to comprehend, in flashes so quick we might miss them if we blink. Fast radio bursts reveal a universe of sudden, concentrated violence, but a quieter discovery has shaken cosmology to its core. It is a ghostly galaxy called NGC 1052 DF2, a diffuse, wispy collection of stars drifting through space. To the eye, it is unremarkable, a faint smudge of light, but when astronomers measured the motions of its stars, they found something that should not exist. The stars were moving slowly, lazily, as if the galaxy itself were barely holding together. According to our fundamental understanding of gravity and galaxies, this gentle motion spelled disaster. The visible mass of stars in DF2 was far too little to generate the gravity needed to keep those stars from flying apart. For decades, the solution to this exact problem has been dark matter, the invisible, mysterious substance that makes up about 85% of the matter in the universe. We cannot see dark matter, but we can feel its gravitational grip. It forms vast, heavy halos around every galaxy we have studied, providing the extra glue that holds fast-spinning stars in place. Dark matter is not just a component of galaxies, it is the cosmic scaffold upon which they are built. Galaxies form when normal matter, the stuff of stars and planets, falls into the gravitational wells created by these immense dark matter halos. This is the standard model of modern cosmology, and then along came DF2. Its stars were moving so slowly that the galaxy required almost no extra gravity to explain their motion. The stunning conclusion, after painstaking measurements, was that this galaxy appeared to have little to no dark matter at all. The discovery sent shockwaves through the scientific community. It was as if you found a towering, magnificent building standing firm, but when you looked at its blueprints, you saw it had no foundation. How could it possibly be standing? For skeptics of dark matter, this was a potential victory. Perhaps our laws of gravity were simply wrong on galactic scales, and no invisible substance was needed. But for the vast majority of cosmologists, DF2 presented a paradox that actually strengthened the case for dark matter's reality. Think of it this way: if dark matter were just a mistake in our understanding of gravity, then its effect should be universal. Every galaxy should show the same discrepancy. Finding a galaxy that perfectly obeys the predictions of Newtonian gravity using only its visible stars is bizarre, but it is also a crucial test. It proves that dark matter is not an inherent flaw in our equations. It is a real, physical substance that can, under extraordinary circumstances, be separated from the stars. So how did DF2 lose its dark matter? The leading theory is one of cosmic robbery. The galaxy lies near a massive elliptical galaxy, a gravitational bully. Billions of years ago, as DF2 passed through the dense cluster environment, the tremendous tidal forces could have ripped away its dark matter halo, leaving behind the delicate puff of stars we see today. The normal matter, being more concentrated and sticky through collisions, clung together while the diffused dark matter was stripped away. This makes DF2 not a refutation of dark matter, but a fascinating fossil, evidence of the violent gravitational interactions that shape galactic evolution. Its existence challenges the foundational narrative that dark matter and stars are inseparable partners. It forces us to refine our models, to understand that the universe has recipes for galaxies that do not follow the standard cookbook. If one galaxy can exist without dark matter, what other strange configurations are floating in the dark, and what do they teach us about the invisible skeleton of the cosmos? The emptiness left by a galaxy stripped of its dark matter is profound, but it pales before a void of truly cosmic proportions. Drifting through the constellation, Boötes lies a region of space so vast and so empty it defies belief. The Boötes void is a spherical chasm roughly 330 million light-years across. To grasp that scale, if you placed our Milky Way at its center, the nearest edge of the void would still be over 150 million light-years away. In a universe we picture as a glittering web of galaxies, this is a hole big enough to swallow thousands of them, and that is precisely the problem. According to our best models of cosmic structure, born from the subtle fluctuations in the early universe, matter should have clumped into a relatively even filigree, a cosmic web with dense clusters, connecting filaments, and inevitable empty spaces called voids. But the Boötes void is not just an empty space, it is a staggering absence. Where we might expect to find tens of thousands of galaxies, surveys have catalogued only a few dozen, scattered like lonely islands in an ocean of nothing. This is not merely a gap in the tapestry, it is a place where the tapestry itself seems to have been torn away. Its existence challenges the very processes that shaped everything we see. How could the primordial soup of the early universe, with its nearly uniform distribution of matter, evolve to leave behind a desert of this magnitude? The tiny quantum seeds that grew into galaxies seem insufficient to explain a vacancy so colossal. It forces astronomers to question whether our understanding of those initial conditions is complete, or if some unknown, powerful force acted to clear this region on an unimaginable scale. One haunting possibility is that the void is not empty by accident but by consequence. Could it be the scar of a past universe-altering event? Some have theorized it might be the result of an intersection with another universe in the multiverse, a collision that swept this region clean. Others wonder if it is evidence of a civilization so advanced it has literally harvested every galaxy within it, a concept so staggering it borders on mythology. Yet the most profound lesson of the Boötes void may be about perspective and probability. In an infinite or near-infinite universe, even the most statistically unlikely structures must appear somewhere. The void might be a cosmic anomaly, a one-in-a-billion fluctuation that just happens to exist within our observable horizon. Its very presence, as unsettling as it is, teaches us that the universe is under no obligation to look uniform from our particular vantage point. It is a monument to the fact that randomness on a grand enough scale can carve out emptiness so deep it challenges our sense of cosmic order. What other improbable structures lie beyond our current view, waiting to redefine what we consider normal? While voids speak of emptiness on a galactic scale, a much smaller mystery was unfolding right in our own cosmic backyard. The Pioneer anomaly is a story of precision, patience, and a ghostly tug that seem to defy the known laws of physics. For decades, as the Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the orbits of the outer planets and into the deep cold of interstellar space, scientists tracking their trajectories noticed something was wrong. The probes were slowing down slightly more than they should have been. It was an almost imperceptible deceleration, a tiny, constant sunward pull equivalent to about 10 billion times weaker than the gravity we feel on Earth. Yet, over millions of miles, this minuscule discrepancy added up, putting the spacecraft about 240,000 miles off their predicted courses. This was not a mistake in the math. Every known force had been accounted for: the gravitational pull of every planet, the subtle pressure of sunlight, even the minuscule thrust from tiny leaks of onboard gas. And still, the anomaly remained, a persistent whisper that our understanding of gravity might be incomplete at the very edges of our own solar system. For years, this unexplained deceleration sparked a firestorm of theoretical possibilities. Could it be evidence of dark matter exerting a local drag? Was it a sign that Einstein's theory of general relativity needed a slight modification over vast distances, a hint of new physics waiting to be discovered. Some even pondered if it was an effect of the spacecraft's own rotation or a yet unknown interaction with the solar wind. The Pioneer anomaly became a classic scientific detective story, a tiny clue pointing to a potentially revolutionary truth hiding in plain sight. The eventual solution, however, was a masterclass in humility and meticulous engineering. A dedicated team of researchers dove into decades-old design documents and telemetry data, painstakingly modeling every conceivable source of force on the aging probes. The culprit, it turned out, was not new physics but old heat. The Pioneer spacecraft were powered by radioactive thermoelectric generators, which produced a significant amount of waste heat. That heat was emitted from the spacecraft's bodies, primarily from the rear-facing electronics panels. Photons, the particles of light and heat, carry a tiny amount of momentum. As these thermal photons radiated away from the spacecraft, they acted like a gentle, continuous thruster pushing ever so slightly back toward the sun. This anisotropic thermal radiation, slightly stronger from the back of the craft than the front, created the precise, constant deceleration that had baffled scientists for so long. The case was closed, a triumph of careful retro-engineering. Yet, the legacy of the Pioneer anomaly is far more profound than its solution. For over 20 years, it stood as a glaring imperfection in our celestial mechanics, a stubborn data point that refused to fit. It demonstrated that even in the well-mapped territory of our solar system, we could still be surprised by the subtle, cumulative effects of forces we thought we understood. It forced a generation of physicists to look harder, to question deeper, and to consider that the next great discovery might not come from the edge of a black hole, but from the gentle glow of a spacecraft's own warmth. That persistent, ghostly tug reminds us that before we can search for monsters in the deep dark, we must first be certain we have accounted for every shadow in our own house. The ghostly tug of the Pioneer anomaly was solved by the mundane glow of spacecraft heat, but a far grander and more unsettling alignment has been found etched into the first light of creation itself. This is the so-called axis of evil, a discovery that makes many cosmologists deeply uncomfortable. It refers to a bizarre and controversial pattern in the cosmic microwave background, that ancient afterglow from the Big Bang. According to our most cherished cosmological principle, the universe should have no preferred direction, no special axis. The variations in this baby picture of the cosmos should be random, like the static on an old television screen. Yet, when scientists analyze the most detailed maps from satellites like Oumuamua and Planck, they find certain large-scale features, the biggest ripples in space-time, that seem oddly aligned with the plane of our own solar system. It is as if the universe's oldest fingerprint is somehow oriented toward our local neighborhood, a coincidence so staggering it defies belief. This alignment is not a visual pattern you could see with your eyes. It is a statistical ghost revealed through complex analysis of the temperature fluctuations across the entire sky. The troubling implication is that our solar system's ecliptic, the flat disk in which Earth and the other planets orbit, appears to be linked to the largest structures in the nascent universe. This directly assaults the cosmological principle of isotropy, the foundational idea that the universe looks the same in all directions from any point. If true, it would mean our place in the cosmos is not random or average, but somehow special, a thought modern science has worked for centuries to dispel. The immediate and rightful suspicion is that we are seeing not a feature of the universe, but a flaw in our measurement, a contamination from our own backyard. Could dust in our solar system or the Milky Way's own magnetic field be imprinting this signal onto the data? Teams have scrutinized this possibility exhaustively, and while some foreground effects can be subtracted, a stubborn, low-level statistical anomaly remains. Its persistence is what fuels both the controversy and the profound unease. The name axis of evil, coined half-jokingly by a physicist, captures the depth of the problem. If this alignment is real, it forces a monumental rethink. One possibility is that it hints at a pre-Big Bang structure, a primordial anisotropy that shaped the infant universe before inflation could smooth it completely away. Another, even more radical idea is that it points to a universe that is not infinite and uniform, but finite and shaped like a hall of mirrors, creating patterns that repeat and align in ways we perceive as strange correlations. For many scientists, the most likely explanation remains a subtle, not yet fully understood systematic error. But the very fact that such a glaring, high-stakes anomaly exists in our most precious cosmological data set is a discovery in itself. It reveals the tension at the heart of exploration, the moment when pristine data from the edge of time seems to hold up a mirror, and we cannot tell if the face we see is the universe's or our own reflection in the glass. What if the ultimate challenge to our reality is not finding something alien, but discovering that our local address is written into the foundation of everything? Far from the subtle alignments of ancient light, our radio telescopes have captured something new and shockingly bold. They are called odd radio circles, or ORCs, and they are exactly that: enormous, faint, perfect circles of radio emission hanging in the dark. They are not galaxies, not supernova remnants, not anything we have seen before. Each one is so vast it could swallow our entire Milky Way galaxy many times over, yet they are invisible to optical telescopes, revealing themselves only in the specific wavelengths of radio light. Their discovery was a complete accident, found in the sweeping surveys of the Australian Square Kilometre Array Pathfinder telescope. Astronomers were mapping the sky for familiar objects when these ghostly rings appeared, not one or two, but several, each a cosmic question mark etched in radio silence. Their perfection is part of the mystery. These are not blobs or smudges, but crisp, circular structures, often with a brighter edge like a bubble shell. They float in intergalactic space, far from the dense hearts of galaxy clusters. The immediate scramble for an explanation has led to a cascade of theories, each more dramatic than the last. One leading idea is that they are the titanic shockwaves from a cataclysm that occurred billions of years ago, perhaps the result of two supermassive black holes merging in the center of a galaxy. Such an event would unleash a tsunami of energy that could propagate outward for eons, creating a spherical wave front we see as a ring. Another possibility is a starburst frenzy on an unimaginable scale, where a galaxy undergoes a period of such intense star formation that the combined stellar winds and supernova explosions blow a colossal, spherical cavity into the surrounding intergalactic gas. Yet the sheer size and isolation of these circles push theorists toward even more exotic frontiers. Could they be the throats of wormholes, theoretical tunnels through space-time, their mouths glowing with radio emission from particles caught in unimaginable gravitational fields? Or perhaps they are the signatures of jets from an active galactic nucleus, but viewed end-on, so the jets are pointing directly at us, creating the illusion of a perfect ring. Some have even ventured that they might be the echoes of a powerful, one-time event like a gamma-ray burst, its radiation slamming into surrounding gas clouds and lighting them up in a circular pattern that persists long after the initial flash is gone. What makes ORCs a fundamental challenge is that they represent an entirely new class of object. In science, the most exciting discoveries are not the ones that fit neatly into existing boxes, but the ones that require us to build a new box entirely. For decades, our catalogues of cosmic phenomena have been relatively stable: galaxies, nebulae, pulsars, quasars. ORCs do not belong in any of those chapters. They are a blank page, a sign that our map of the universe is still missing entire continents of structure. Their silent, ghostly rings tell us that the cosmos is still capable of architecture on a scale, and in a form we have not yet dreamed of, hiding in plain sight, waiting only for us to look in the right way. While odd radio circles stretch across millions of light years, a recent discovery was hiding in our own galactic neighborhood, small enough to earn a mythical name. This is the unicorn, a black hole of almost impossibly low mass, lurking just 1,500 light-years away. It is not devouring stars or warping space-time with violent jets. Instead, it is quiet, dark, and detectable only by the subtle, rhythmic dance of a nearby red giant star. Astronomers noticed this companion star was being stretched and pulled, its light periodically shifting as if tugged by an invisible partner. The culprit's mass was calculated to be just about 3 times that of our Sun. In the realm of black holes, that is tiny, skirting the very edge of what we thought was possible. This discovery is a monumental challenge to our understanding of how stars die. We have well-established models for the creation of stellar mass black holes. A massive star, many times heavier than the Sun, exhausts its nuclear fuel, collapses under its own gravity, and triggers a supernova explosion. What remains is a black hole, typically with a mass between 5 and 15 times that of the Sun. On the other end, we have neutron stars, the dense cores left behind by slightly smaller stars, which max out at about 2.2 solar masses. Between these two categories lies a perplexing gap, a so-called mass gap where, according to theory, no compact object should easily form. The unicorn sits squarely in that forbidden zone. Its existence forces a critical question: how did it get there? Did a star somehow collapse directly into a black hole without a supernova, leaving behind this small, silent remnant? Or could it be the product of 2 neutron stars merging, creating an object too heavy to be a neutron star but lighter than a typical black hole? Finding the unicorn suggests this mass gap might not be empty at all, but populated by a hidden family of small black holes we have simply lacked the methods to see. They do not emit the telltale X-rays of a black hole actively feeding, so they remain ghosts detectable only through their gravitational influence on companion stars. This opens an entirely new window in astronomy. If such a small black hole exists so close by, how many more are drifting unseen through the galaxy? Their population could rewrite the story of stellar death, revealing that the final moments of stars are far more diverse and subtle than our models of brilliant supernovas suggest. The unicorn is a quiet whisper in the data, proving that sometimes the most revolutionary discoveries are not the largest or loudest, but the small, shy ones that have been hiding in plain sight all along. The quiet, small black holes hiding in our galaxy are one thing, but the James Webb Space Telescope has now found giants in the nursery. These are galaxies from the universe's infancy, seen as they were just a few 100 million years after the Big Bang. According to all our models, this era should be filled with small, chaotic, and immature collections of stars, the first fragile building blocks of future giants. What Webb found instead was a shocking collection of massive, fully formed, and tranquil galaxies. They are far too big, far too soon. It is like walking into a kindergarten classroom and finding a group of fully grown adults sitting at the tiny desk. The light from these galaxies has traveled for over 13 billion years to reach us, meaning we are seeing them in their extreme youth. Yet their stars are already old, having formed and settled into stable, disk-like shapes with a calmness that speaks of billions of years of quiet evolution. The numbers are what break the models. Some of these galaxies appear to have masses tens of billions of times that of our Sun, and one, frighteningly named ZF13, seems to have a mass rivaling our present-day Milky Way, all when the universe was only 300 million years old. Our best simulations of cosmic growth simply cannot make something that big that fast. Dark matter halos need time to coalesce to attract normal gas, which then needs time to cool, collapse, and form stars. The process is meant to be gradual, a slow assembly over billions of years. Webb's galaxies suggest a universe that worked in fast forward, assembling cosmic cities in the blink of a cosmic eye. This discovery forces a profound reevaluation. One possibility is that our understanding of the very first stars is wrong. Perhaps the earliest stellar generations were unimaginably efficient, forming from pristine gas without heavy elements and reaching colossal sizes, living fast and dying young to seed galaxies with mature stars almost instantly. Another, more unsettling idea is that our cosmic timeline is off. Could the universe be older than we think? This would require a fundamental rewrite of our most sacred cosmological data, the expansion rate and the age derived from the cosmic microwave background. Or it might point to new, unknown physics in the early universe, a form of rapid structure formation driven by something beyond our standard model of dark matter and gravity. Each potential solution unravels a different thread in the tapestry of cosmology. Webb's impossible galaxies are not just distant points of light, they are stopwatches frozen in the deep past, and they are all ticking far too fast. They tell us that the story of how everything came to be, from the first spark to the grand spirals we see today, is missing crucial, perhaps revolutionary chapters. Deep in the cosmic past, infant galaxies grew impossibly fast, but the present universe holds worlds forged in conditions of equally staggering extremity. One such world circles the star 55 Cancri, just 40 light-years away, a super-Earth we have named 55 Cancri E. This is no rocky planet like our own, built from silicates and iron. Based on its density and the carbon-rich chemistry of its star system, astronomers believe this world is a colossal diamond, a planet-sized jewel adrift in the void. Imagine a world with a mass nearly 8 times that of Earth, compressed into a radius only twice as large, orbiting so close to its sun that a single year lasts a mere 18 hours. The gravitational pressure in its interior is unimaginable, crushing carbon atoms into the crystalline structure of diamond, potentially forming a layer hundreds of miles thick. This is not a metaphor, it is a likely geological reality, a world where the bedrock is literal gemstone. The surface conditions are a vision of hellish beauty. Because it is tidally locked, one face permanently blistered by its star, temperatures on the dayside soar above 2,500 degrees Celsius, hot enough to melt most metals and vaporize rock. Early observations suggested the planet might be covered in global oceans, but not of water, of lava. Superheated silicate rock would exist in a perpetual, churning molten state, a seething, incandescent sea beneath a carbon-rich sky. More recent data from the James Webb Space Telescope, however, has added a stunning twist. It detected signs of an atmosphere, one that appears to be bubbling violently from within the planet itself. This atmosphere is not primordial, it is being actively replenished, possibly by a geologically hyperactive interior where immense pressures force gases like carbon monoxide or carbon dioxide up through cracks in the diamond crust. The planet may be literally outgassing its own shroud, a process that could be periodically stripped away by the intense stellar radiation, only to be rebuilt again. The existence of 55 Cancri E fundamentally rewrites the catalogue of planetary possibilities. Our solar system taught us a simple taxonomy: small rocky worlds close to the sun, gas giants farther out. But here is a world that breaks all the local rules. It proves that a planet's composition is a direct reflection of the raw materials available in its stellar nursery. In a system rich in carbon over oxygen, the chemistry of planet formation favors carbon compounds like graphite and diamond over the silicate rocks we are made of. This diamond super-Earth challenges the very definition of a terrestrial planet, revealing a universe where the building blocks of worlds can be as exotic as gemstones and the outcomes as strange as a glittering orb bathed in molten rock. If such a world can exist so close by, what other impossible geologies are waiting to be found, and how many more chapters of planetary science remain completely unwritten? A diamond world orbits a sun, but some planets have no sun at all. They are the rogue planets, dark, lonely worlds cast adrift in the interstellar void, belonging to no star and no solar system. They wander the galaxy in perpetual night, lit only by the faint glow of distant stars or the volcanic heat of their own cooling cores. For centuries, our definition of a planet was inextricably linked to a star, a celestial body bound by gravity to orbit a sun. The discovery of these free-floating worlds shatters that simple definition and reveals a hidden population in the darkness, detecting something that emits almost no light and has no star to give it away is one of astronomy's greatest challenges. Scientists use two primary methods. The first is gravitational microlensing. When a rogue planet drifts precisely between Earth and a distant background star, its gravity acts as a tiny lens, bending and magnifying the star's light for a brief period, often just a few hours or days. This creates a characteristic brightening in the star, a telltale spike that reveals the planet's mass and presence. It is like finding a single, invisible marble by watching how it distorts the light of a street lamp far behind it. The second method is even more direct, searching for the faint, residual heat of young rogue planets. These are worlds recently ejected from their stellar nurseries, still glowing warmly from the energy of their violent formation. Powerful infrared telescopes can sometimes pick up this dim thermal signature, especially if the planet is massive, more like a failed star known as a brown dwarf. So how do planets go rogue? Their origin stories are tales of cosmic chaos. Some are likely formed in the same way stars are, from collapsing clouds of gas and dust that simply never gathered enough mass to ignite nuclear fusion, becoming Jupiter-like orphans from birth. But most are thought to be the victims of gravitational violence. In the crowded, unstable environment of a young star system, gravitational interactions between giant planets can be catastrophic. One world may be flung out of its orbit entirely, ejected into the deep freeze of interstellar space at tremendous speed, becoming a permanent exile. Others might be torn from their orbits during a close encounter with a passing star, a cosmic robbery that leaves a planet homeless. The sheer abundance of these worlds is what truly rewrites our galactic maps. Estimates from microlensing surveys suggest there could be billions, perhaps even trillions, of rogue planets in our Milky Way alone, potentially outnumbering stars by a staggering margin. This invisible archipelago of dark worlds challenges our every assumption about planetary systems. We once pictured solar systems as stable, clockwork arrangements with planets neatly orbiting a central sun. The rogue planets force us to see them as dynamic and often violent places, where gravitational billiards is a common game and ejection is a frequent fate. It means that for every stable system like our own, there may be countless failed systems, their planets scattered to the winds. These lonely wanderers also raise profound questions about the potential for life. A rogue planet with a thick hydrogen atmosphere could trap geothermal heat from a radioactive core, creating subsurface oceans of liquid water shielded by an icy crust, a dark, internal sea warmed from within. In such a place, life might not need a sun, drawing energy from hydrothermal vents on an ocean floor in eternal darkness. The galaxy may be filled with such hidden, warm abysses, life-bearing worlds that never see a sunrise. The discovery of these nomads forces us to expand our imagination of what a planet can be. It is not just an object that orbits, it is a world that exists alone in the perfect quiet between the stars. The dark wanderers challenge our ideas of home, but a world we thought we knew holds a faint, flickering signal that refuses to be explained. This is the methane on Mars, a ghostly whisper in the thin, cold air of the red planet. For decades, our robotic emissaries have sampled the Martian atmosphere, and they have detected sporadic, unpredictable plumes of methane gas. These are not constant features, but fleeting bursts that appear and vanish, a puzzle written in a gas that should not be there in such quantities. On Earth, the vast majority of methane in our atmosphere is produced by living organisms, from microbes in wetlands to the digestive systems of livestock. It is a classic biosignature, a chemical flag of life. Finding it on Mars immediately raises the heart-stopping question: are we smelling the breath of Martian microbes? The detections themselves are a story of scientific tension. The Curiosity rover, tirelessly exploring Gale Crater, has repeatedly sniffed methane at the surface, sometimes in background traces, other times in sharp, tenfold spikes. Yet, the European Space Agency's Trace Gas Orbiter, a sophisticated satellite designed specifically to map atmospheric gases from above, has often reported no methane at all in the global atmosphere. This discrepancy is not a failure, it is a crucial clue. It suggests the methane is not mixing evenly into the Martian air, but is being released in localized, transient bursts that the rover happens to drive through, and that dissipate before the orbiter can see them from high altitude. The challenge to reality here is profound. It forces us to confront Mars not as a static, geologically dead museum, but as a world that might still be subtly active, breathing in ways we are only beginning to perceive. If the methane is not from life, then what geological process could be producing it? One possibility involves water rock chemistry. Certain minerals, like olivine, can react with water and carbon dioxide in a process called serpentinization, producing methane as a byproduct. If liquid water exists in subsurface aquifers, this slow, abiotic chemistry could be feeding methane into the atmosphere. Another idea points to ancient methane, trapped in ice-like structures called clathrates deep underground, occasionally released when the Martian soil is disturbed by impacts or seismic activity. Yet the sporadic nature of the releases is tricky for these geological models to fully explain. The alternative, of course, is the one that redefines everything. If the source is biological, it would likely be subsurface, where hypothetical microbes, called methanogens, could be eking out an existence in briny pockets of water deep below the frozen surface, protected from harsh radiation. They would not need sunlight, deriving energy from the chemical reaction between hydrogen and carbon dioxide, and exhaling methane as waste. This discovery does not prove life exists on Mars, but it utterly shatters the narrative of Mars as a completely dead world. It transforms the planet from a passive landscape into a place of potential hidden activity, a realm where chemistry, or perhaps even biology, is still writing its subtle story. The intermittent whiff of methane is a siren call, a reminder that the search for life is not a search for cities or signals, but for the quiet, chemical rustling in the dark soil of another world. The faint chemical whisper from Mars hints at hidden processes, but Saturn broadcasts its strangeness in a shout of pure geometry. At the gas giant's north pole, a storm rages that is unlike any other in the solar system, a hurricane over 20,000 miles wide with a shape so precise it seems artificial. This is Saturn's hexagon, a six-sided jet stream of clouds that has remained locked in place for decades, perhaps centuries, a perfect geometric figure etched into the atmosphere of a planet. The contrast with our own world is absolute. On Earth, weather is chaotic, a study in swirling curves and unpredictable fronts. Our polar vortices are roughly circular, shifting and pulsing with the seasons. Saturn's hexagon is a rigid, rotating polygon. Its six nearly straight sides, sharper than any natural feature has a right to be. It is a colossal, spinning honeycomb cell wrapped around the pole, a structure so stable it has outlasted every human civilization that has ever tried to observe it. The challenge to reality here is not about life or ancient light, but about the fundamental behavior of fluids on a planetary scale. How can a storm, a system of churning gas, maintain such razor-sharp, angular boundaries for so long? The answer lies in an elegant dance of fluid dynamics, a concept you can test in a simple laboratory. When a fluid rotates in a circular basin and a smaller, inner circle rotates at a different speed, the interaction between these two layers can spontaneously generate standing waves. These waves are not gentle swells but sharp polygonal patterns in the fluid's flow. Scientists believe this is precisely what is happening deep within Saturn's atmosphere. The planet's internal heat drives massive convection currents, creating a difference in rotational speed between different atmospheric bands. This shear creates instability, and under the right conditions, that instability locks into a stable, six-sided standing wave pattern that propagates upward to shape the visible cloud tops. It is a natural resonance, like the pure tone that rings from a wine glass when you rub its rim. Saturn's entire northern hemisphere is the glass, and the hexagon is its enduring note. Yet, understanding the basic principle does not erase the wonder or the mystery. Why six sides? Why has this specific pattern persisted while others have not? Laboratory experiments can produce polygons with 3 to 8 sides, but they are often transient. Saturn's hexagon is a permanent fixture, a monument to the unique conditions within that specific gas giant. Its existence tells us that the physics of planetary atmospheres can produce order of a kind we never anticipated, a mathematical purity emerging from apparent chaos. It forces us to look at every swirling storm on every gas giant and wonder what hidden geometries might lie beneath the clouds, what other perfect shapes the universe prefers when it spins a world of a certain size at a certain speed under a certain light. Saturn's perfect hexagon reveals a universe of hidden geometry, but another class of world replaces rigid angles with a single, all-encompassing element. These are the water worlds, planets like JWST a super-Earth 48 light-years away that may hold no land at all. This planet is a dark, steamy orb, larger than Earth but significantly lighter. Its low density can only be explained if a huge fraction of its mass is not rock but water. Imagine a world with a rocky, metallic core like Earth's, but then enveloped by an ocean not miles deep but hundreds of miles deep. A global, uninterrupted abyss where the very concept of a shoreline is alien, and the pressure at depth transforms water into substances you would never recognize. This is where our Earth-centric intuition fails completely. We think of water in 3 familiar states: solid ice, liquid water, and gaseous steam. Under the crushing pressures at the bottom of a planetary ocean, water enters exotic, alien phases. It can become hot ice, forms like Ice 6 or Ice 7, where the water molecules are locked into crystalline structures denser than liquid water, not from cold but from immense pressure. You could have a layer of solid water resting on the seafloor, heated to hundreds of degrees, with a global ocean of liquid water floating above it. Further down, near the rocky core, the water might become a supercritical fluid, a seething, corrosive substance that is neither liquid nor gas, but possesses properties of both, capable of dissolving minerals and creating a bizarre, churning chemical soup. The existence of such worlds forces a radical expansion of what we consider a habitable environment. We have long focused on the Goldilocks zone, the orbital distance where a planet is just right for liquid water on its surface. But a water world turns this idea inside out. The surface of JWST is likely a scorching 400 degrees Fahrenheit, capped by a thick, opaque atmosphere of steam and hydrogen. For life as we know it, the surface is a sterilizing pressure cooker. The true habitable zone on such a planet is not on the surface, but deep within it, in a subsurface layer where pressures and temperatures might allow for liquid water in contact with a mineral-rich core. In the eternal darkness of that deep ocean, life would not rely on sunlight, but on chemical energy from hydrothermal vents, much like the ecosystems found in Earth's deepest ocean trenches. These worlds suggest that a planet does not need Earth-like continents or a thin atmosphere to be a cradle for biology. It only needs a stable, long-lived interface between liquid water, rock, and energy. The galaxy could be filled with such hidden aquatic abysses, each a potential universe of life utterly isolated from the stars, thriving in a warm, dark sea under a sky of crushing ice or superheated steam. They are a profound lesson in cosmic humility, proving that the template for life is not a pale blue dot, but perhaps a deep black ocean. The deep, dark oceans of water worlds speak of isolation, but our own galaxy tells a story of a spectacular and ancient merger. Stellar archaeology, the science of reading the history of stars, has uncovered a violent event in the Milky Way's past, a cosmic feast we now call the Gaia-Enceladus merger. This discovery shatters the long-held view of galaxies as serene, isolated islands, revealing instead a history of brutal collisions and galactic cannibalism. The evidence is written in the motions and chemistry of stars that should not be here. Using data from the European Space Agency's Gaia spacecraft, which maps the positions and velocities of over 1 billion stars with exquisite precision, astronomers noticed something strange. A large population of stars in our galactic halo, the sparse spherical cloud of ancient stars surrounding the Milky Way's disk, were moving in a distinct retrograde pattern. They were orbiting the galactic center in the opposite direction to the vast majority of stars, like cars driving the wrong way on a cosmic highway. More than just their motion gave them away. These stellar interlopers also had a different chemical fingerprint. Stars born in the same cloud at the same time share a similar composition, like siblings. The stars in the Milky Way's thick disk where our Sun resides are rich in heavier elements or metals forged in the hearts of earlier stellar generations. The retrograde stars, however, were metal poor, a sign of great antiquity. They were relics from a much earlier, more primitive time in cosmic history. The only explanation that fits is a dramatic collision. Roughly 10 billion years ago, when the Milky Way was still young and forming, a smaller, gas-rich dwarf galaxy, now nicknamed Gaia-Enceladus, came too close. The two galaxies did not simply pass by, they slammed together and merged. The gravitational chaos of this event would have been titanic, scattering stars from both galaxies into the halo and violently churning the Milky Way's primordial gas disk, triggering a massive wave of new star formation that helped build the thick disk we see today. The retrograde stars are the surviving population from that devoured dwarf galaxy, the digested remains of a galactic meal. This discovery fundamentally rewrites the biography of our cosmic home. We are not the product of quiet, solitary evolution. The Milky Way, and likely every large galaxy we see, was built through a hierarchical process of violent assembly, growing by consuming smaller neighbors. Our galaxy has a cannibalistic past, and the stars in its halo are the fossils of that ancient feast. It forces us to see the night sky not as a static painting, but as a dynamic, ever-changing sculpture where the gentle spiral we admire today was forged in a long-ago fire of collision and chaos. What other ancient mergers are written in the motions of stars we have yet to measure, and what did our galaxy look like before this transformative encounter? Galactic cannibalism paints a violent history, but some planets are actively dissolving before our eyes. This is HD 209458b, nicknamed Osiris, a world so close to its star it is being blasted into a spectral stream. It was the first exoplanet ever detected transiting its star, and the first to have its atmosphere directly analyzed, but its most stunning feature is a tail 190,000 miles long, a vast plume of gas bleeding off into space. Osiris is the archetypal hot Jupiter, a gas giant orbiting its sun at a mere 1/20th the distance of Mercury from our sun. Here, temperatures on the star-facing side soar above 1,000 degrees Celsius, hot enough to vaporize iron. At such proximity, the star's intense radiation and powerful stellar wind act like a cosmic blowtorch, stripping the planet's outer atmosphere layer by layer. Hydrogen, helium, and heavier elements are superheated to the point where they achieve escape velocity, boiling off into the void. This process, atmospheric evaporation, is not a gentle leak but a raging, supersonic exodus. The escaping gas is then caught by the stellar wind and sculpted into a magnificent, comet-like tail that trails behind the planet in its orbit, a permanent scar of its disintegration. We are witnessing a planet in a state of slow, spectacular demise. The significance of Osiris extends far beyond its own tragic fate. It serves as a natural laboratory for understanding one of the most critical processes in planetary science: how planets lose their skies. This phenomenon is not unique to blistering hot Jupiters. Our own Mercury is a barren rock largely because its proximity to the Sun and weak gravity allowed its early atmosphere to be stripped away. Mars, smaller and with a weaker magnetic field than Earth, lost most of its thick atmosphere over billions of years to the solar wind, transforming from a potentially wet world into a frozen desert. By studying the extreme, accelerated evaporation on Osiris, we can calibrate the models that describe these slower, more subtle processes across the galaxy. It answers fundamental questions about the diversity of worlds we see. Why are there so few planets that fill the gap between Earth's size and Neptune's? One compelling theory is the evaporation valley, where sub-Neptunes orbiting too close to their stars have their thick, primordial hydrogen envelopes completely stripped away, leaving behind only the dense, rocky core, a process we might be seeing in its final, dramatic act with Osiris. This planet's magnificent tail is more than a cosmic curiosity. It is an hourglass. It measures the finite lifespan of a world under an unforgiving sun, and in doing so, teaches us about the birth, evolution, and ultimate erosion of atmospheres everywhere. If a giant can be dissolved into a stream of stardust, what does that mean for the long-term survival of any world, including our own, in the relentless flow of cosmic time? While planets evaporate and galaxies collide, the ultimate fate of the cosmos was rewritten by a discovery of pure, chilling geometry. In the late 1990s, two independent teams of astronomers were studying distant supernova, the titanic explosions of dying stars, to measure how fast the universe was expanding. They expected to find a slowdown. The collective gravity of all the matter in the cosmos, they reasoned, should be acting like a cosmic brake, gradually pulling on the fabric of space and decelerating the great outward rush that began with the Big Bang. The data they collected told a story that was exactly, terrifyingly opposite. The most distant supernova, whose light had been traveling for billions of years, were fainter than they should have been. This dimness could only mean one thing: those ancient exploding stars were farther away than our models predicted. The expansion of the universe was not slowing down. It was speeding up. Some mysterious, repulsive force was stretching the very vacuum of space itself, pushing galaxies apart at an ever-increasing rate. This force earned a name that captures our profound ignorance: dark energy. The discovery was so shocking, so contrary to all expectation, that the team spent years checking and rechecking for errors, from cosmic dust to the intrinsic properties of the supernova themselves. The evidence held firm. In 2011, the leaders of these projects were awarded the Nobel Prize in Physics for a finding that overturned a century of cosmological assumption. Dark energy is not just another mystery, it is the dominant component of our universe, making up roughly 68% of everything that is. It is not matter, dark or otherwise. It is a property of empty space, a latent energy woven into the fabric of nothingness that causes space itself to expand. The more space there is, the more of this repulsive energy exists, creating a runaway feedback loop that accelerates the expansion forever. This single discovery reframes the entire cosmic story and our place within it. For billions of years, gravity fought a valiant battle, pulling galaxies together into clusters and filaments, building the great web of structure we see today. But around 5 billion years ago, dark energy's influence crossed a threshold. It began to overwhelm gravity's pull on the largest scales. Now, the universe is in the grip of this anti-gravity, and its victory is absolute. The implications for cosmic fate are bleakly magnificent. In an accelerating universe, the distant future is one of profound isolation. Galaxies not already bound by gravity to our local group will eventually be pushed away by the expanding space between us. Their light, stretched beyond detection, will fade from view. Trillions of years from now, astronomers in our galaxy will look out into a black, empty void. The cosmic microwave background faded to nothing, with no evidence that other galaxies ever existed. The universe will become a collection of isolated island universes, drifting apart into eternal, silent darkness. Dark energy is the biggest unsolved problem in physics because it strikes at the heart of our two most successful yet incompatible theories, quantum mechanics and general relativity. Calculating the energy of the vacuum from quantum theory gives a number that is wrong by a factor of 1 followed by 120 zeros, the worst prediction in the history of science. This means we are fundamentally missing something deep, a new theory that unifies the very large and the very small. Is dark energy a constant, as Einstein once proposed and then discarded as his greatest blunder? Or is it a dynamic field that could change over time, perhaps even rip apart atoms in a far future cataclysm called the Big Rip? We simply do not know. This force, discovered by measuring the faint glow of dying stars, dictates the destiny of everything, and we have only just begun to ask it the right questions. Dark energy dictates a future of silent isolation, but the present cosmos thrums with a deep, inaudible rhythm. This is the gravitational wave background, a constant, low-frequency hum resonating through the fabric of spacetime itself. For years, we have detected the sharp, transient chirps from collisions between stellar mass black holes and neutron stars, each event a brief, violent crescendo. The background is different. It is not a single crash, but the collective murmur of millions, perhaps billions, of supermassive black hole pairs, each weighing billions of suns, slowly circling each other in the hearts of distant galaxies. Their immense, ponderous dance sends out ripples in spacetime that overlap and combine into a permanent, universe-filling drone, a bass note so deep it takes years of observation to hear. The discovery of this hum, announced in 2023, did not come from a single telescope but from turning our entire galaxy into one. Scientists used pulsars, the rapidly spinning corpses of dead stars that emit beams of radio waves with the precision of cosmic metronomes. By monitoring dozens of these pulsars across the Milky Way for over 15 years, researchers watched for minuscule, correlated shifts in their ticking. The passing of a gravitational wave stretches and compresses space, causing the pulses to arrive at Earth a fraction of a second early or late. The painstaking analysis revealed a pattern, a common signal affecting all the pulsars in concert, the signature of the long-predicted background hum. This is more than just a new sound from space. It is an entirely new sense. For all of human history, we have explored the cosmos using light, from visible rays to radio waves and X-rays. Gravitational waves are a fundamental departure. They are ripples in the geometry of the universe, allowing us to feel events that are completely dark to traditional astronomy. The gravitational wave background opens a window into the chaotic, merging history of galaxies. Every large galaxy is believed to host a supermassive black hole at its center. When galaxies collide and merge, as the Gaia Enceladus story showed us, their central black holes are eventually drawn together, entering a slow, spiraling courtship that can last for eons. It is the final, fading chorus of these cosmic mergers that we are now beginning to hear. The hum challenges our models of the universe's most violent events because it is louder than many theorists expected. The strength of the signal suggests that supermassive black holes merge more frequently, or perhaps more efficiently, than our simulations predicted. Do they stall in their final approach, or is there some unknown mechanism that helps them shed energy and coalesce? The background hum is a census of the universe's most monstrous inhabitants, and the initial returns suggest our head count may have been off. Listening to this primordial drone forces us to confront the universe not as a static picture, but as a dynamic, vibrating entity. Every cubic light-year of space is being subtly flexed by this endless symphony of collisions from the deep past. It is the sound of cosmic structure being built, the groaning of space-time under the weight of infinite gravity. As we learn to tune our instruments to this new frequency, what other choirs will we hear in the hum, and what secrets of the galaxy's violent adolescence are written in its waves? That cosmic hum is a chorus from the depths of time, but a single, quiet star much closer to home sings a tune that threatens to unravel time itself. This is HD 140283, the Methuselah star, a faint, ancient sun just 190 light-years away. When astronomers measured its age using our most sophisticated models of stellar evolution, they arrived at a number that is simply impossible: 14.5 billion years old. The universe, according to our best measurements from the cosmic microwave background, is 13.8 billion years old. This star, by the numbers, appears to be nearly 1 billion years older than the cosmos that birthed it. It is a paradox written in starlight, a chronological impossibility that stares back at us from our own galactic neighborhood. The age of a star is not read from a birth certificate, it is pieced together from forensic clues. For HD 140283, the most critical clue is its chemical composition. This star is what astronomers call a metal-poor subgiant. The term metal here means any element heavier than hydrogen or helium. In the early universe, only hydrogen, helium, and trace lithium existed. All other elements like carbon, oxygen, and iron were forged later in the cores of stars and scattered by supernova explosions. A star born later will inherit this enriched material. The Methuselah star is remarkably deficient in these heavier elements, a clear sign it formed from primordial gas in the universe's first few 100 million years. Its current brightness and temperature place it at a specific, advanced stage in its life cycle, burning through the last of its hydrogen. By plugging these properties, its composition, luminosity, and temperature into our stellar models, we get that staggering age estimate. The tension this creates is not a sign that our models are completely broken, but a signal that they are being pushed to their absolute limits. The uncertainty in the star's age is about 800 million years, a vast window that just barely overlaps with the age of the universe. The key to shrinking that window lies in pinning down the star's distance with perfect precision, because a tiny error in distance leads to a huge error in calculated luminosity and thus age. Recent data from the Gaia spacecraft has refined the distance, bringing the star's estimated age down to around 13.5 billion years, much closer to, but still potentially older than, the universe. This persistent edge of the paradox forces a profound question: which pillar of our understanding bends first? Do we need to revise the universe's age? The cosmic microwave background calculation is considered one of the most robust in all of science, supported by multiple independent lines of evidence. Tweaking it to accommodate this one star would create cascading conflicts elsewhere. The more likely adjustment is to our models of the very first stars. What if the earliest stellar generations had different internal processes? Perhaps they rotated faster or mixed their nuclear fuel more efficiently, which would allow them to burn longer and appear younger than they truly are in our current models. Or maybe the Methuselah star lost mass during its long life in a way we haven't accounted for, altering its evolution. This single, ancient point of light is a stress test for our entire cosmic timeline. It reminds us that the first chapters of the universe's story are written in the aging hearts of these stellar relics, and we are still learning how to translate their language. The Methuselah star does not prove our cosmology wrong. It proves that the dawn of time is more complex, more subtle, and more wondrous than our elegant equations have yet captured. The ancient heartbeat of a star is a clock, but a young system nearby has broken time's symmetry entirely. In the constellation of Orion, a cosmic ballet of staggering complexity unfolds around a star system named JW Orionis. Here, not one but 3 stars are locked in a gravitational dance, 2 orbiting each other closely while a third circles the pair at a greater distance. This alone is a recipe for chaos, but the true wonder lies in the disk of gas and dust that swirls around them all, a birthplace for planets that has been twisted into a shape from a cosmic nightmare. Most protoplanetary disks are flat, like a spinning vinyl record, a smooth sheet of material where planets can coalesce in orderly orbits. The disk around JW Orionis is nothing like that. Observations from the Atacama Large Millimeter Array have revealed it is dramatically warped, broken into distinct, tilted rings that look like a celestial hula hoop caught in a storm. At its center is a vast, empty gap, wide enough to hold the entire orbit of Mercury within our own solar system. And within that gap, the data suggests a planet or planets are already forming, a world growing up in a gravitational maelstrom. This is a place where the standard rules of planet formation are not just bent, they are shattered. In a single star system like our own, the process is relatively serene. Dust grains in a flat disk collide and stick, building pebbles, then planetesimals, and finally planets, all orbiting peacefully in the same plane. In the triple star chaos of JW Orionis, the competing gravitational tugs from all 3 suns constantly pull and torque the disk, heating it through friction, warping its structure, and ripping it into misaligned rings. This creates an environment of extreme violence and opportunity. The immense gap in the disk is likely carved by the gravitational influence of a young, massive planet. Its presence acts like a cosmic plow, clearing a path through the dust and gas. But for that planet to form in the first place, it had to overcome forces that should, in theory, tear any accumulating material apart. How can a world assemble itself when the very nursery it is born in is being violently shaken? The answer may lie in the disk's broken structure. Those distinct, tilted rings could act as isolated sanctuaries, pockets of relative calm within the storm where material can safely clump together away from the most extreme gravitational shear. A planet forming in the gap between these rings would experience a surreal sky. Depending on its location in its orbit, it might see 1, 2, or all 3 suns in its heavens in a cycle of eternal, complex sunrises and sunsets. Some days might have multiple shadows, while others plunge into the deep chill of a single star's distant light. The discovery of this system forces a complete rethink of where and how planets can exist. We once thought multi-star systems were too unstable to host stable orbits, yet here we have evidence of worlds forming in the most dynamically hostile environment imaginable. It suggests that planet formation is not a delicate process requiring quiet solitude, but a robust, almost stubborn force of nature that can proceed even in the heart of gravitational pandemonium. If planets can coalesce here within the twisted disk of a triple star system, then the potential for worlds across the galaxy is exponentially greater. Every chaotic, multi-star dance could be hiding its own family of planets, born from the wreckage of a broken disk, orbiting in paths we are only beginning to imagine. The chaotic birth of planets in a triple star system stretches our imagination of cosmic architecture, but what if we found a structure built not by gravity but by intelligence? The search for such artifacts has moved from science fiction into rigorous data analysis, focusing on a specific, staggering idea, the Dyson sphere. This hypothetical megastructure, proposed by physicist Freeman Dyson in the 1960s, is the signature of a civilization that has mastered its star. A Type II civilization on the Kardashev scale would not live on planets alone, but would harness the total energy output of its sun. To do this, it might construct a vast swarm of orbiting collectors, a shell or a ring of habitats and solar panels that captures starlight and irradiates the waste heat as infrared radiation. For decades, this was a purely theoretical exercise. Now, with the flood of data from the European Space Agency's Gaia mission, which has mapped the positions, motions, and brightness of nearly 2 billion stars, the hunt has become real. Scientists are no longer just imagining, they are systematically sifting through the galaxy, looking for the telltale signature of a star wrapped in a technological shroud. The method is elegant in its simplicity. A star partially enclosed by a Dyson swarm would appear oddly dim in visible light because some of that light is being captured. But energy cannot be created or destroyed, only transformed. The captured starlight would be used and then emitted as waste heat at longer infrared wavelengths. Therefore, the key signature is a star that is anomalously faint for its type, yet glows with an excess of infrared warmth. It is like finding a light bulb that seems too dim, but when you hold your hand near it, it feels as hot as a brighter bulb should be. Something is blocking the visible light and irradiating the energy as heat. The Gaia mission, combined with infrared surveys from telescopes like WISE, provides the perfect dataset to search for these mismatches. Researchers have developed algorithms to scan for stars whose visible light and infrared emissions are out of sync in ways that cannot be easily explained by natural dust clouds or protoplanetary disks. They are looking for the unnatural, for a thermodynamic signature that screams of purpose and engineering. This is not a search for radio signals or laser pulses. It is a search for the thermodynamic footprint of a civilization so advanced its most obvious feature is a star that looks wrong. The candidates that have emerged are fascinating puzzles. These are stars that show the exact infrared excess predicted for a partial Dyson swarm, but also exhibit other peculiarities that keep astronomers cautious. Could the infrared glow be from a rare, thick ring of warm dust very close to the star, or perhaps from a recent, catastrophic planetary collision that created a colossal cloud of debris? Each natural explanation must be exhausted before any whisper of the artificial can be entertained. Yet, the very act of searching is a profound shift in our approach to the cosmos. It forces us to define what we mean by a technosignature, moving beyond communication to the detection of industry on a stellar scale. It challenges us to think in geologic and cosmic time. A Dyson structure would not be built in a century but over millennia, and it might exist in a state of perpetual construction or repair. We might be seeing not a finished shell, but a fragmented swarm, a work in progress that has been ongoing for 100,000 years. Finding even a single, compelling candidate would force a monumental reckoning. It would mean that intelligence is not just a fleeting whisper in the biological dark, but a force capable of re-engineering the fundamental power sources of a galaxy. It would tell us that the long-term destiny of a thinking species is to become a visible part of the cosmic landscape, to leave a mark on the very stars themselves. The quiet, data-driven search through Gaia's star charts is perhaps the most ambitious archaeological dig in history, sifting not through soil but through starlight, looking for the fingerprints of gods in the infrared glow of suns. The search for cosmic architects leads us to the edge of a different kind of abyss, one where the fundamental laws of reality dissolve into paradox. This is the black hole information paradox, a conflict so deep it strikes at the heart of physics itself. The problem begins with a simple question: what happens to the information about an object when it falls into a black hole? In our everyday world, information is always preserved. If you burn a book, the ash and smoke may seem like chaos, but in principle, a being with perfect knowledge of physics could reverse the process, reconstructing the book from the scattered particles. Quantum mechanics, the rulebook for the very small, insists on this principle. Information cannot be destroyed, only scrambled. General relativity, Einstein's theory of gravity that governs black holes, tells a different story. It describes a black hole as a region of space where gravity is so intense that nothing, not even light, can escape. The boundary of no return is the event horizon. According to pure general relativity, if you throw a book or a star or an entire planet into a black hole, it is simply gone, swallowed by a singularity, a point of infinite density where our laws of physics break down. The information about what made up that object, the arrangement of its atoms, its history, seems to be erased from the universe. This creates an irreconcilable war between our two most successful theories. Stephen Hawking brought this conflict into sharp focus in the 1970s. He showed that black holes are not completely black. Due to quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow now called Hawking radiation. This radiation, however, is purely thermal, like the heat from a stove. It carries no information about what fell in. If a black hole evaporates completely over eons, leaving behind only this featureless radiation, then the information about everything it ever consumed is lost forever. This violates the core tenet of quantum mechanics. The paradox suggests that one of our foundational theories is wrong, or at least incomplete. Resolving it has forced physicists to propose ideas that reshape our concept of reality. One radical proposal is the firewall hypothesis. It suggests that the event horizon is not a smooth gateway but a searing wall of high-energy particles. Anything crossing it would be instantly incinerated. This firewall would preserve information by preventing anything from actually entering the black hole in the first place, but it violates Einstein's principle that crossing the event horizon should be uneventful for the falling observer. Another, more elegant solution comes from the holographic principle. This mind-bending idea proposes that all the information about what is inside a black hole is not lost, but encoded on its two-dimensional event horizon like a cosmic fingerprint. The three-dimensional interior is a projection of that information, much like a hologram where a three-dimensional image is stored on a flat, two-dimensional surface. In this view, when the black hole evaporates, the information is not destroyed but is imprinted onto the Hawking radiation in an incredibly complex, scrambled way. The information was on the surface all along, we just did not know how to read it. This paradox is more than a theoretical puzzle, it is a stress test for a theory of everything. Black holes are the ultimate laboratories, places where gravity is strong and quantum effects cannot be ignored. To understand what happens there, we must forge a new physics that unites the very large and the very small. The fate of a single bit of information falling into the dark tells us that our universe might be far stranger than it appears, a holographic projection where the deepest truths are written on the boundaries of nothingness. The black hole information paradox reveals a deep crack in our physical laws, but another fundamental flaw lies in the very emptiness we take for granted. According to quantum field theory, what we call a perfect vacuum is not empty at all. It is a seething, bubbling sea of potential, a foam of virtual particles that wink in and out of existence in an endless dance governed by the uncertainty principle. These fleeting pairs of particles and antiparticles borrow energy from the vacuum itself, existing for a sliver of a moment before annihilating each other and returning the energy. This quantum vacuum is not still, it is alive with transient energy, and this energy, the zero-point energy of empty space, should have a gravitational effect. It should act as a constant source of repulsive gravity, pushing the universe apart. This sounds remarkably familiar. It is the exact description of dark energy, the mysterious force driving the accelerated expansion of the cosmos. The connection seems perfect, an elegant solution. The quantum vacuum energy could be the engine of dark energy, but when physicists perform the calculation, the result is not just wrong, it is catastrophically, incomprehensibly wrong. The theoretical prediction for the energy density of the vacuum exceeds the observed value of dark energy by a factor of 10 to the power of 120. That is the number 1 followed by 120 zeros. It is a discrepancy so vast it is often called the worst prediction in the history of science. To grasp the scale of this error, imagine predicting the distance from Earth to the nearest star and being off by a margin greater than the size of the entire observable universe. This is not a small tuning problem. It is a screaming alarm that something in our most fundamental understanding of reality is either missing or profoundly mistaken. The challenge here is not just to explain dark energy, but to explain why it is so absurdly, unexpectedly tiny. Why is the vacuum energy not inflating the universe into a meaningless, instantaneous froth? This forces physicists to consider desperate and beautiful ideas. One possibility is that we live in a multiverse, a vast landscape of universes, each with different values for the vacuum energy. In almost all of these universes, the energy is too high, causing them to expand or collapse instantly, never forming stars or atoms. We, by necessity, find ourselves in one of the rare, freakishly balanced universes where the vacuum energy is just low enough to allow galaxies and life to form. This anthropic reasoning feels to many like a philosophical retreat rather than a scientific answer. Another avenue suggests that a new, yet undiscovered symmetry in nature cancels out the vacuum energy to near zero, or that the energy of the vacuum somehow gravitates differently than ordinary matter, a modification to Einstein's equations. The staggering mismatch between prediction and observation is a permanent thorn in the side of theoretical physics. It tells us that the quantum world and the cosmic world are speaking different languages, and our translation between them is missing a crucial dictionary. The quiet, empty space between stars, it seems, holds the loudest unanswered question of all. Our struggle to reconcile the vacuum's energy is a battle of theories, but the hunt for a single, elusive particle is a quest for a cornerstone of reality. This is the magnetic monopole, a hypothetical particle that is a solitary north or south magnetic pole, a magnet with only one end. In our everyday experience, magnetism always comes in pairs. Break a bar magnet in half and you do not get an isolated north and an isolated south. You get two smaller magnets, each with its own north and south pole. This duality is baked into Maxwell's equations of electromagnetism and observed in every magnet on Earth. Yet, for nearly a century, theoretical physics has whispered that a solitary pole should exist. The reason is one of profound symmetry. Electricity and magnetism are two sides of the same coin, unified into the electromagnetic force. We have solitary electric charges, the positive proton and the negative electron. So why should magnetism be different? The absence of a magnetic charge feels like an aesthetic flaw in the universe's design, a broken symmetry that hints at a deeper truth. Finding just one magnetic monopole would be a revolution on par with the discovery of the electron. Its existence is a direct prediction of grand unified theories, ambitious frameworks that seek to merge the electromagnetic force with the weak and strong nuclear forces into a single, elegant interaction that ruled the universe in its first fleeting moments after the Big Bang. These theories suggest that in the searing heat of that primordial instant, the symmetry between electricity and magnetism was perfect, and monopoles were as common as particles. As the universe expanded and cooled, a phase transition occurred like water freezing into ice, and most of these monopoles became incredibly rare, frozen into the fabric of spacetime as topological defects. Finding one would be a fossil from that first trillionth of a second, tangible proof of unification. Beyond confirming our most ambitious theories, the monopole holds the key to a mystery we take for granted: why electric charge comes in discrete, quantized packages. Why is the charge of an electron exactly equal and opposite to that of a proton? In a beautiful piece of mathematics, the existence of even a single magnetic monopole in the universe would force electric charge to be quantized. The monopole's magnetic charge would act as a fundamental unit, and all electric charges would be integer multiples of it. This would explain a fundamental feature of nature that currently has no deeper explanation. The quest, however, has yielded only profound silence. Scientists have searched for monopoles everywhere, from the debris of particle colliders to the depths of ancient mineral deposits and even in moon rocks. They have looked for their trails in cloud chambers and for their distinctive signatures in vast underground detectors. The continued absence of magnetic monopoles is in itself a powerful discovery. It has forced theoretical physics down specific paths, ruling out certain versions of grand unified theories and placing stringent limits on the conditions of the early universe. It tells us that if monopoles were created in the Big Bang, something must have happened to dilute their numbers to an almost undetectable level, a process that itself reshapes our models of cosmic inflation. This relentless, fruitless search is not a failure but a guiding constraint. It exemplifies how science often advances not just by what we find, but by what we do not find in places we were certain it should be. The universe is holding back this one perfect piece of symmetry, and in that withholding, it challenges us to look deeper, to build better theories, and to wonder if the next revolution might be hiding not in the chaos of a collision, but in the quiet patience of a detector waiting for a ghost that may never come. The magnetic monopole's absence is a puzzle of symmetry, but another idea suggests the very laws we seek to unify are not laws at all, but lines of code. This is the simulation hypothesis, the startling proposition that our universe, with all its stars, planets, and conscious minds, is not base reality, but an artificial construct, a simulation running on some unfathomable computer in a higher plane of existence. It is not a new philosophical thought experiment, but one that has gained traction in the modern era, championed by figures like Elon Musk and supported by strands of reasoning that pull from both computer science and quantum physics. The central argument begins with a simple projection of technological progress. If a civilization advances far enough, it would likely develop the capability to run vast, detailed simulations of its own history or of entirely fictional worlds. Given enough time and computational resources, such a civilization might run not one, but billions of these simulations, each populated with conscious, simulated beings who believe their world is real. In this scenario, the odds are overwhelming that any given conscious being, like you or me, would not be in the original, base reality, but in one of the countless simulations. We are far more likely to be artificial minds in a digital ancestor simulation than biological minds in the one true universe. This statistical reasoning is compelling, but the hypothesis draws deeper intrigue from the observed nature of reality itself. Quantum mechanics, the rulebook for the smallest scales, presents a world that is eerily digital. Energy is quantized, coming in discrete packets. Particles exist in probabilistic states until observed, a process that feels less like passive discovery and more like rendering, where properties are only calculated when something is looking. The universe appears to have a fundamental resolution limit, a Planck length and Planck time, below which the concepts of space and time lose meaning. This is reminiscent of a pixelated screen where zooming in too far reveals the underlying grid. Even the speed of light, the universe's ultimate speed limit, can be seen as a processing constraint, a maximum clock rate for the cosmic computer to prevent computational overload. The challenge this poses to objective reality is absolute. If we are in a simulation, then everything we perceive, from the taste of coffee to the pain of loss, from the grandeur of a galaxy to the laws of physics themselves, is a data stream, a convincing illusion generated for our conscious experience. The search for a theory of everything becomes the search for the source code. Glitches in the matrix, like the cold spot or the axis of evil, might not be cosmic anomalies but artifacts, rounding errors, or even deliberate Easter eggs left by the programmers. The Fermi paradox finds a chillingly elegant solution. the simulation is simply not populated with other civilizations, or they are non-player characters. Our drive to explore and understand the universe is not a noble quest for truth, but a programmed curiosity, a feature designed to make the simulation engaging for its inhabitants. Yet, the hypothesis is not without its profound counterarguments. The most significant is the sheer, staggering computational power required to simulate every particle, every force, and every conscious thought in a universe of 93 billion light-years. Simulating reality at the quantum level for every atom in every star seems an impossible burden, even for a super-advanced civilization. Proponents counter that a clever simulation would not need to render everything in perfect detail all the time. It would use optimization techniques like a video game that only renders the graphics a player is currently looking at. Distant stars might be low-resolution placeholders, their light pre-calculated. The quantum weirdness only resolves when observed because that is when the simulation bothers to do the calculation. This idea turns the observer effect from a mystery into an efficiency protocol. Whether you find the simulation hypothesis plausible or preposterous, its value is undeniable. It forces the ultimate Copernican revolution, demoting us not just from the center of the universe, but from the center of reality itself. It challenges us to define what real even means. If a simulated mind feels joy, creates art, and ponders its own existence, is its experience any less valid? The hypothesis reframes our entire scientific endeavor. We are no longer just physicists and astronomers, we are reverse engineers, trying to crack the operating system of a possible simulation, looking for the signatures of the programmer in the mathematical elegance of the code. It asks the most unsettling question of all: if this is a simulation, what is the purpose of the experiment, and what happens when we finally figure it out? The unsettling thought of a simulated reality dissolves into a phenomenon that proves our universe is fundamentally, undeniably connected. This is quantum entanglement, a link so intimate and instantaneous it defies every classical intuition about space and time. Two particles, like electrons or photons, can be created or interact in such a way that their properties become intertwined. From that moment on, no matter how far apart they are separated, they remain a single, unified quantum system. Measure the spin of one particle here on Earth, and the spin of its partner, perhaps on the other side of the galaxy, is instantly determined. This connection happens faster than light, with no signal passing between them. Albert Einstein famously derided this as spooky action at a distance, a sign that quantum theory must be incomplete because it seemed to violate the cosmic speed limit set by his own theory of relativity. For decades, it was a philosophical debate, a strange quirk of the math. Then came the experiments. In the 1970s and 80s, physicists like John Bell devised a way to test whether this spookiness was real or if some hidden variables were secretly controlling the particles all along. The experiments, growing more precise over the years, have delivered a clear and stunning verdict: entanglement is real. When scientists measure entangled particles, their results are correlated in ways that are impossible if the particles were independent entities carrying predetermined instructions. The choice of what to measure on one particle seems to reach out and touch its partner across the void instantly. This shatters two pillars of our classical worldview: locality and realism. Locality is the idea that objects are only influenced by their immediate surroundings, and that any influence must travel through space, taking time. Entanglement obliterates locality, showing that influence can be non-local, acting across vast distances with no travel time. Realism is the assumption that particles have definite properties, like a specific spin, before we measure them. Entanglement suggests that these properties do not exist in a definite state until the act of measurement forces a decision, and that decision is communicated to the entangled partner immediately. The universe, at its most fundamental level, is not a collection of separate, isolated objects. it is a vast, shimmering web of instantaneous connections. What does this mean for our understanding of reality? It suggests that separation is an illusion of scale. The space between stars, between galaxies, may be vast to us, but to the quantum substrate of the universe, that distance might be meaningless. Particles that have interacted remain part of a whole, their identities forever linked. This is not magic, it is woven into the geometry of space-time itself. Some interpretations propose that entangled particles are not communicating faster than light, but that they are simply accessing a deeper layer of reality where they were never truly separated to begin with. The implications ripple outward, fueling dreams of unhackable quantum encryption and powerful quantum computers, but the deepest implication is philosophical. We are all made of entangled particles, remnants of the same primordial fire. In a very real, physical sense, the universe is not a place where things happen in isolation. It is a single, breathtakingly complex entity, where a measurement made here echoes instantly in the fabric of everything, everywhere. Entanglement reveals a universe stitched together by invisible threads, but what if the fabric itself could be torn and rewoven into its opposite? This is the theory of white holes, the hypothetical time reversal of a black hole. If a black hole is a cosmic drain from which nothing escapes, a white hole is a cosmic fountain from which nothing can enter. It is a region of space-time that violently expels matter and energy, while its event horizon acts as a one-way exit door, repelling any attempt to cross from the outside. The mathematics of general relativity, in their beautiful symmetry, allow for such a solution. Just as the equations predict the crushing gravity of a black hole, they also permit its mirror image, a singularity that only gives, never receives. While no white hole has ever been observed, their potential existence forces us to confront the most stubborn arrow in our universe, the arrow of time itself. In our everyday experience, time flows inexorably forward. Entropy increases, eggs scramble but never unscramble, and we remember the past, not the future. Black holes fit neatly into this forward flow. They are the ultimate endpoints of gravitational collapse, consumers of order. A white hole, however, would run this film in reverse. It would be an origin point, a source of new matter and energy erupting into the cosmos, a violation of the thermodynamic tendency toward disorder. How could such a thing ever come to be? One compelling, if speculative, idea ties white holes directly to the fate of black holes. In the Hawking radiation process, a black hole slowly evaporates over eons. Some physicists, like Carlo Rovelli, suggest that at the very end of this evaporation, when the black hole has shrunk to a microscopic scale, quantum gravitational effects might prevent it from vanishing entirely. Instead, it could undergo a quantum bounce, a transition where the collapsing geometry rebounds into an expanding one, effectively turning the black hole inside out and becoming a white hole. In this view, every black hole could be the birth canal for a new, microscopic universe, with its Big Bang appearing as a white hole eruption in our own. This white hole would not be a stable object, but a brief, explosive event, spewing out the transformed remains of everything the black hole ever consumed. The implications for cosmology are staggering. Could our own Big Bang have been the white hole eruption from a black hole in a parent universe? This idea, part of the theory of cosmological natural selection, paints a picture of a multiverse where universes reproduce through black hole collapses and white hole births. Each universe inherits slightly tweaked physical constants from its parent, leading to an evolutionary pressure for universes that are efficient at producing black holes and thus offspring. It is a breathtakingly grand cycle of cosmic life and death. Even if they are not cosmic parents, white holes challenge our understanding of singularities. In a black hole, matter is crushed to infinite density at the center, a point where our laws of physics break down. A white hole singularity would be a past singularity, a point from which the universe emerges rather than one into which it falls. Resolving what happens at these points requires a theory of quantum gravity, and white holes provide a crucial testing ground. They force us to ask if time itself can loop or reverse at the quantum level. Could the interior of a black hole connect via a wormhole to the exploding interior of a white hole in another time or place? While such ideas remain in the realm of theory, they illustrate how the simple act of running the equations backward can shatter our linear perception of cause and effect. The universe may not have a single, simple beginning, but a complex tapestry of endings that are also beginnings, where every sink is also a potential source, and every death holds the seed of a new reality. A conscious mind could simply blink into being from the chaos of empty space. This is the unsettling premise of the Boltzmann brain, a thought experiment so strange it threatens to invalidate our entire cosmic story. It begins not with astronomy, but with a 19th century understanding of heat and disorder. Physicist Ludwig Boltzmann proposed that the universe's apparent order, like stars and planets, could be a rare but inevitable fluctuation in a cosmos that is, on the whole, a formless sea of maximum entropy or disorder. In an infinitely old and vast universe, every possible arrangement of particles, no matter how unlikely, will eventually occur by random chance. Given enough time, the atoms in a void could spontaneously arrange themselves into a perfect replica of the Mona Lisa, or a steaming cup of coffee, or a living, thinking human brain. The Boltzmann brain is the ultimate such fluctuation, a self-aware consciousness with a lifetime of false memories, complete with the sensory illusion of a body and an entire universe popping into existence for just a moment before dissolving back into the chaos. The terrifying statistical argument goes like this. In an eternally expanding universe dominated by dark energy, space becomes an increasingly cold, empty, and uniform void over trillions upon trillions of years. The probability of any complex structure forming becomes vanishingly small, but it never hits zero. The spontaneous fluctuation of a single, isolated brain with its intricate neural patterns is astronomically unlikely. But the spontaneous fluctuation of an entire ordered universe with hundreds of billions of galaxies, each with billions of stars and planets, is so much more unlikely that it makes the single brain look commonplace by comparison. Therefore, if the universe lasts forever in this empty state, the number of Boltzmann brains that will randomly fluctuate into existence should vastly, overwhelmingly outnumber the number of minds that evolved naturally in a universe like ours. By the raw math of probability, you and I are far more likely to be one of these fleeting, disembodied illusions, experiencing a brief fantasy of reality, than a product of 13.8 billion years of cosmic evolution. This conclusion is so patently absurd that physicists recoil from it, not because it feels wrong, but because it uses the logic of their own theories to undermine the very reality those theories describe. If we accept the premise of an eternal, expanding universe, the Boltzmann brain becomes a statistical inevitability. The challenge, then, is not to prove the brains exist, but to prove why our universe cannot be the kind of place where they become the dominant form of consciousness. This forces cosmology into a corner. One escape route is to argue that our universe is not eternal and will not endure in a dark energy-dominated state forever. Perhaps dark energy decays, or perhaps the universe will eventually collapse in a big crunch or rip apart in a big rip, putting a finite expiration date on the cosmic vacuum and cutting off the time available for these bizarre fluctuations. Another, more profound implication is that our universe has a very special, low-entropy beginning. The Big Bang was not a random fluctuation from a prior high-entropy state, but a singular event that set the arrow of time and established a vast reservoir of order to be slowly spent over eons. In this view, we are not a random accident in an eternal void, but part of a specific, structured story with a beginning that itself requires explanation. The Boltzmann brain paradox ultimately is not about brains at all. It is a stark warning sign that our extrapolations of current physics into the infinite future lead to logical nonsense. It tells us that our understanding of cosmic probability, time, and the nature of consciousness itself is still dangerously incomplete. Are we the legitimate heirs of a grand cosmic evolution, or just ghosts in the machine, momentary glitches in an endless, silent dark? The answer depends on what kind of universe we truly live in, and whether eternity is a canvas for miracles or for madness. The maddening paradox of the Boltzmann brain forces a confrontation with the nature of information itself, a puzzle that finds its most elegant and radical solution in the final discovery. The holographic principle is not just another theory, it is a complete reimagining of the universe's architecture, suggesting that everything we perceive as three-dimensional reality is a holographic projection from a two-dimensional surface. This idea emerges from the very edge of a black hole, from the paradox of information that seems to vanish into the singularity. Physicists realize that the information about everything swallowed by a black hole is not lost inside, but is somehow encoded on its event horizon, the spherical boundary of no return. The three-dimensional interior, with all its crushing complexity, is perfectly described by quantum bits of information painted onto the two-dimensional surface like a cosmic tattoo. The holographic principle takes this stunning insight and applies it to the entire cosmos. It proposes that our universe, with its stars, galaxies, and the space between them, is not fundamentally three-dimensional. All the information needed to describe every particle, every force, and every event within the volume of space you occupy right now could be encoded on the two-dimensional boundary that surrounds that volume, like the information for a three-dimensional hologram stored on a flat, two-dimensional film. To grasp this, think of a credit card hologram. The flat, shiny sticker holds all the data necessary to project a three-dimensional image that seems to float in space when you tilt it. The holographic principle suggests the universe operates on the same logic, but at the most fundamental level. The three-dimensional world we move through, with its depth and solidity, is the projection. The true reality, the source code, exists on a distant, two-dimensional surface at the edge of the observable universe. This is not a metaphor about simulation. It is a serious proposal within string theory and quantum gravity to resolve the conflict between general relativity and quantum mechanics. It mathematically demonstrates that a theory of gravity in a three-dimensional volume is equivalent to a quantum field theory without gravity operating on its two-dimensional boundary. In essence, gravity and the third dimension are emergent phenomena, illusions that arise from the complex interactions of quantum information on a lower dimensional screen. The implications for our perception of reality are dizzying. It means you, the room you are in, the planet beneath you, are all a magnificent illusion of depth conjured from a flat cosmic canvas. The feeling of moving through space is the experience of that encoded information being translated and rendered in real time. It explains why the universe has a finite amount of information, a maximum entropy, just as a hologram has a maximum resolution based on the pixels available on its film. This principle provides a potential escape from the Boltzmann brain paradox. In a holographic universe, random, complex fluctuations like an isolated brain are not just unlikely, they are computationally forbidden. The boundary of the universe has limited information storage, and a fully detailed, consistent three-dimensional reality like ours uses up that storage in a specific, efficient way. There is simply not enough capacity on the cosmic film to waste on an infinite number of transient, self-aware glitches. We are not a random fluctuation, but part of the coherent projection. The holographic principle challenges the most basic ingredient of our experience, dimension itself. We are creatures who instinctively think in terms of length, width, and height. But this theory tells us that depth is a derived concept, a shadow play cast by information dancing on the walls of reality. It suggests that if we could ever learn to read the quantum script written on the boundary of space, we would hold the complete story of the cosmos from the Big Bang to the farthest galaxy in a form we can barely imagine. The universe is not what it seems. It is not a container but a hologram, and we are the shimmering image within it. From the holographic edge of reality, we have traveled a cosmos reshaped. 35 discoveries, each a key turning a lock in a door we did not know was there. We felt the ghostly tug of the Great Attractor and the silent scream of the wow signal. We stood before galaxies without dark matter and voids of impossible nothingness. We witnessed planets of diamond and stars older than time, felt the chill of the cosmic cold spot and the hum of colliding universes in the gravitational wave background. We have followed the trail of evaporating worlds and pondered the simulated nature of our own minds. Each finding, from the quantum entanglement linking all things to the holographic code that may underpin everything, does more than add to a list. It actively dismantles a comfortable assumption. It replaces a settled fact with a profound question. The universe is not a static museum for us to tour, but a living argument, a debate written in starlight and shadow, where every answer unravels to reveal a deeper, more beautiful mystery. This journey should fill us not with arrogance, but with a deep and necessary humility. We are cosmic beginners, piecing together a story far grander and stranger than our ancestors could have dreamed. The very laws we take as fixed may be local ordinances, the constants of nature might be variables, and our place is almost certainly not central or special. This humility, however, is the engine of all true exploration. It is the reason to look harder, to think deeper, to build better telescopes and more daring theories. The future of space discovery has never been more thrilling. New instruments like the Vera Rubin Observatory will scan the entire sky every few nights, catching transient events we now miss. The Nancy Grace Roman Space Telescope will hunt for dark energy's fingerprints, while next-generation gravitational wave detectors will listen for the whispers of the very first black holes. We stand on the threshold of knowing where the next data point could be the one that rewrites the textbook, so the journey does not end here. It continues with every new observation, every question asked in the comments below. Tell us which of these 35 realities was the first to fracture for you. Was it the silent, empty Boötes void or the ticking clock of the Methuselah star? Share your thoughts, join the conversation, and if this voyage to the edge of understanding resonated with you, like this video and subscribe. Together, we will keep looking into the dark, ready for the next discovery that reminds us the universe is always more wonderful and more mysterious than we suppose.